My name is Charles Baker. I was the LRO thermal lead. Heritage instruments typically have been used in Mars and beyond type missions in the past. There haven't been that many missions to Mercury, Venus, the Moon. And those three planetary bodies have rather severe thermal environments that end up driving instrument design all the way through. So on LRO, for instance, the 7 instruments that were picked for LRO didn't really have a thermal design at conception. And that tended to be a problem moving forward from conception through their early development. As one lunar day is around 28 Earth days, and the Moon doesn't have an atmosphere, there's very little heat exchange from the hot side of the Moon to the cold side of the Moon. In addition, it has a very low albedo, so most of the sun is absorbed by the soil right where it comes onto the Moon, and the soil gets very hot, effectively causing a very high IR environment that's difficult to mitigate thermally. The lunar environment is the only other planet in the solar system with probably a worse thermal environment is Mercury. So it's typically considered number 2 on the solar system for thermal severity. Typically with cameras, you're very concerned about CCD temperatures, and the CCDs are typically within an aperture. If you're looking at a relatively cold planet such as Mars or further on in the solar system, you have an inherent radiator out the aperture. When you look at something like the Moon, where the temperature is varying from hundreds of degrees C to 100 Kelvin in one orbit, those designs typically don't stand up to that type of environment and need modification with different radiator paths than their heritage instruments had. We had to work directly with the instrument teams to redevelop their mechanical and thermal packaging to accommodate this rather severe environment, and do it in a way that it worked with the overall LRO system. The optical bench that 3 of the instruments were attached to also added some complexity in that it couldn't really take any heat for them. Just because they are interplanetary instruments and their overall mass is fairly low by necessity of delta V budgets and such, there wasn't a tremendous amount of staff and personnel working on each individual instrument. Because these teams were fairly small, they generally didn't have the thermal expertise that bigger missions might have. So inherent to Discovery class missions like LRO, you really have to make sure that the overall mission level thermal is giving as much help as necessary to the instrument teams so they understand what the problems are and understand where solutions might be thermally. My name is Charles Baker. I was the LRO thermal lead. In order to mitigate a lot of the thermal concerns of missions like LRO, it is important to, in addition to exchange models, but have face-to-face discussions about how exactly the models run and what the drivers might be for the instrument itself and what the drivers are from the spacecraft side into the instrument, and how we can modify mechanical and thermal designs to make the ultimate thermal job easier. With model exchanges and with site-to-site visits, on LRO, we were out at the facilities sometime after instrument accommodation review, prior to PDR, prior to CDR. We were at CDR, we were at CDR peer reviews, and were intimately involved in the ultimate qualification. So the key is to go visit the instruments often and early so that you can start this very long process of what is the ultimate system design for thermal in a way that it can be successful at that moment of truth when you launch. In order to mitigate the risk of these instruments with their heritage designs being able to work in the LRO mission thermal environment, the very first step was simply to recognize that this was an issue, and we needed to aggressively put resources, both mass and manpower, into helping to develop designs that would work in this extreme environment. Generally, when you look at mission integrators, they pull in thermal models from instruments fairly late, and often treat the instrument teams like, yeah, they probably know what they're doing and probably have the right answer because, hey, they're responsible. We kind of took the opposite approach, saying it's too severe of an environment to simply leave it to chance that the teams were going to arrive at the right answer. So we pulled in, we provided a interface from our end to them fairly early and expected them to provide teams, or we expected their team to provide models back to us right around the PDR timeframe so that we could also do predicts with their model attached to our model. We developed some fairly high-level documentation where we told them exactly what we expected from the models and what we expected from the interface. And the good thing about the documents wasn't necessarily that both of us followed the letter of the law, but it spurred ideas on both sides as to what we might be worried about going forward. And it kind of kept front and center where the concern areas might be, and we were able to quickly assess each instrument individually and hone in on which portions needed the most attention. On the various model inputs that we received from the instrument teams, two of the teams we discovered errors as late as CDR that would have caused a instrument failure had they not been discovered. And again, this was coming from the instrument vendors to us, taking the model, looking carefully at all the linkages, all the powers, and realizing some of them just didn't make physical sense. So this model exchange has to be done often enough that you're able to uncover those errors prior to them really being a mission driver and causing the instrument to fail during its qualification, or worse yet, on orbit. If you look at thermal, typically the systems approach is that all of the thermal model outputs are relatively conservative, therefore we don't need to hold much margin. But when you looked at the instruments on the scale of LRO, their power numbers were fairly small. Their design details, such as where harness was running, as well as other blockages from the spacecraft or from blankets, really required additional margins, such as larger heaters and larger radiators, so that things could be tailored right during instrument thermal balance to optimize performance of the instruments. We modified one of the instruments at instrument thermal balance, modified one of the other instruments' radiator size at orbiter thermal balance, simply due to the way that it was performing right in the chamber, and new requirements that came along which lowered its operational temperature limit. My name is Charles Baker. I was the LRO thermal lead. Lessons learned is the word heritage only applies to thermal if the actual environment that the instrument was used in last was more severe than the environment that's being baseline for. If it is less severe, then there needs to be resources put into an early model exchanges, early technical exchanges to help develop the thermal subsystem so that it can handle the more severe environment. Sometimes the instrument teams themselves oversell their own sense of security with respect to thermal. Many instrument teams are composed of people that don't come from the thermal subsystem and don't really understand how this is different. Thermal isn't typically seen as a mission driver, but if you have a mission like LRO where thermal is so severe, it becomes this hidden driver, and it's important to make sure that concern is disseminated and exposed as early as possible. For small instrument teams, analysis type subsystems like thermal tend to really not have the rigor that they would on a very large instrument that's made by a large institution. So the right people generally aren't looking at the problems and realizing their severity. Just because it's a $20 million instrument as opposed to a $60 million instrument, if the environment is severe enough, you've got to put substantial resources into thermal, independent of what percentage it was of the instrument cost. It is actually pretty close to a showstopper for the Diviner instrument because of its orientation, because of its heritage design. Its margins are very, very low in the LRO mission. It happens to be working successfully on LRO, but it was pretty close to being a showstopper earlier on, just due to its own constraints being a heritage mechanical system. Now, whether thermal can be a mission enabler or mission disabler, very much so. I mean, it all depends when the thermal surprise is discovered. When is that moment discovered where a temperature on a component exceeds anything that it's been qualified to before? If that moment is early enough, you can engineer your way out of it. If it's late, then it has major mission implementation or major mission schedule impacts in that parts need to be redesigned and the entire program grinds to a halt very late in INT. Thermal is one of the last things that ever gets tested, and it's also one of the most rigorous tests, and it's also one where most of the problems with respect to operations are discovered.